The rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is equal to 20 times sine t squared over 35 cubic feet per hour. T is measured in hours, and it's on the interval 0 to 8 inclusive. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by d of t is equal to that expression, cubic feet per hour, for the interval 0 to 8 inclusive. There are 30 cubic feet of water in the pipe at time t equals 0. Part A asks, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval 0 to 8 inclusive? Because we are given the function r that models the rate at which rainwater is flowing into a drain pipe, in order to find how much rainwater flowed into the drain pipe, all we need to do is take the integral of r of t from the beginning time interval, 0, to the end time interval, 8. So this would be equal to the definite integral from 0 to 8 of 20 times sine of t squared over 35. Because question 1 is a calculator problem, all you would need to do is insert this expression into your graphing calculator to get 76.570. Part B asks, is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for your answer. The keywords increasing and decreasing tells us that we should focus on the net rate of change to answer this part. If the amount of water in the pipe is increasing, that means that its net rate of change is positive, whereas if it was decreasing, that would mean its net rate of change is negative. Remember that our rates of change in this problem are modeled by r of t and d of t. So the net rate of change at time equals to 3 would be r of 3, the amount of water being gained in that instant, subtracted from d of 3, the amount of water being drained at that instant. Using our calculators, we can approximate this as 5.0863 subtracted by 5.4, which is equal to around negative 0.314. Because the net rate of change that we found is negative, that must mean that there is more water being lost than there is being gained at time equals to 3. So therefore we can conclude that the amount of water at t equals to 3 is decreasing. Part C reads, at what time t on the interval from 0 to 8 inclusive is the amount of water in the pipe at a minimum? Justify your answer. Remember that absolute minima and maxima can only occur at two places, at the endpoints if it's an inclusive domain, or at the critical points, which is where the first derivative is 0 or does not exist. So for part C, we know that the minimum could occur at when t is equal to 0 or when t is equal to 8, because those are our two endpoints. Now let's see if there are any critical points to test. Critical points occur when the derivative is 0 or does not exist, and the derivative is the instantaneous rate of change of a function. So the derivative for this question would actually be r of t minus d of t, because this is the net change being gained, and this is the net change being lost. So like we used in the previous problem, if we subtract r of t from d of t, that shows us our instantaneous net change at a particular point. So let's set this expression equal to 0 or does not exist. Now a quick glance at these functions shows that there's no place where they don't exist, because this is a cubic polynomial and r of t is a sinoid graph. So we can rule out that does not exist, and we're left with when r of t minus d of t is 0. So if we graph this expression and then use the 0 function on our calculator, we can find that the 0 of r of t minus d of t is at when t is equal to around 3.272. So let's add that to the list of points we have to try. Now all there's left to do is to test these 3 points and see how much water is in the pipe at each of these instances. Let's call the amount of water in the pipe at time t w of t. Now we can model w of t as the definite integral from 0 to t of r of x, which is the same thing as r of t, subtracted from d of x, which is the same thing as d of t, dx, plus the initial amount of water the problem gives us, the 30 cubic feet of water. So this is plus 30. So basically, this definite integral models the amount of water that we gain or lose based on our net change from the starting time to time t. Then we add that to the amount of water that we started with. So basically what this equation is saying is that the amount of water at time t is the sum of the initial amount of water present in the pipe plus the amount of water that we gained or lost during the interval from 0 to t. Now we can plug this expression into our calculators, substituting this t for the test point that we want. So if we plug in w of 0, we know that this would just be our initial value, so w of 0 is equal to 30. If we plug in w of 8, it turns out to be around 48.5. So w of 8 is 48.5. And then if we plug in w of 2.72, this turns out to be 28.0. So we can see from these values that the amount of water inside the pipe would actually be the minimum when time is equal to 2.72. Part D asks, the pipe can hold 50 cubic feet of water before overflowing. For t is greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write, but do not solve, an equation involving one or more integrals that give the time w when the pipes begin to overflow. So we know that the maximum the pipe can hold is 50 cubic feet of water. And we also know that we begin with 30 cubic feet of water. So for part D, we can write 30 plus some integral should be equal to 50. That's when the pipe will begin to overflow. We had already established from previous parts of the problem that the net change in the amount of water that was gained or lost, can be modeled by the integral from 0 to any time of r of t, the rate at which water was gained, minus d of t, the rate at which water is being lost, dt. And the question wants you to use w as the time when the water begins to overflow. So what this answer is basically saying is that the initial amount of water in the pipe plus the amount of water you accumulate from the initial position, the initial time, to time w will cause the pipe to overflow because it will hit the 50 cubic feet of water. Johanna jogs along a straight path. For the interval 0 to 40 inclusive, Johanna's velocity is given by a differentiable function v. Select values of v of t, where t is measured in minutes and v of t is measured in meters per second, are given in the table above. Part A asks, Use the data in the table to estimate the value of v prime of 16. Recall that a function's instantaneous rate of change is its derivative, and the way to estimate an instantaneous rate of change given select data points from the original function is to use the average rate of change, or the slope of the function. Looking at our data set, we can see that t equals 16 fits perfectly in the middle of t equals 12 and t equals 20. So let's use those values when determining the slope at point t equals 16. So let's use the slope formula to estimate v prime of 16. So this is v of 20 minus v of 12 over 20 minus 12, which equals your 240 subtracted from your 200, which is 40, over 8, which is equal to 5. You have your meters per minute divided by your minutes, which makes this meters per minute squared. So for the sake of the 2019-2020 AP Calculus AB test, we will not go over Part B because the test does not require you to know how to take the integral of motion functions. We will, however, go over Part C. Part C says, Bob is riding his bicycle along the same path. For the interval 0 to 10 inclusive, Bob's velocity is modeled by this expression, where t is measured in minutes, and b of t is measured in meters per minute. Find Bob's acceleration at time t equals to 5. So in the question, it states that b of t models Bob's velocity, and it asks you to find Bob's acceleration. Well, we know the relationship between velocity, v of t, and acceleration, a of t, is the derivative of the velocity function. The derivative of the velocity function gives the acceleration function. So by that logic, that must mean the derivative of b of t equals the acceleration of Bob. So like the acceleration of Bob at time t. So let's take the derivative of b of t. We know that b of t equals t cubed minus 6 times t squared plus 300. Now we can use the power rule on each individual term. The power rule states that we move this 3 in front, and then we subtract 1 from the exponent. So b prime of t would equal 3 times t raised to the 3 minus 1 power, which is just 2, subtracted by 6 times 2 is 12, raised to the 2 minus 1 equals first power. And we know that the derivative of a constant equals 0. Now, the question wants us to find Bob's acceleration at time t equals 5. So let's plug that into this acceleration equation. This becomes b prime of 5 is equal to 3 times 5 raised to the second power, subtracted from 12 times 5 plus 0. Now it just evolves into an algebra problem, or actually a basic arithmetic problem. This becomes 25 times 3, which is 75, subtracted from your 12 times 5, which is 60. So 75 minus 60 is equal to 15. And we've already established that your velocity, that your acceleration is measured in units meters per minute squared. Like with Part B, we will not be covering Part D in this video either because it involves average values of motion problems as well as integrals of motion problems, neither of which will be covered in your AP exam this year. So let's move on to question 4. Question 4 gives us the differential equation dy over dx is equal to 2x minus y. Part A asks, on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. Remember that the slope field is a graphical representation of the function's slope at each point. Also remember that dy dx gives us the slope of a function. So because they gave us a differential equation, we can solve for each point's slope by plugging in the x and y values. So let's do that. At the point 0, -1, dy dx, or a slope, is 2 times the x value, 0, minus the y value, which is -1. So this slope is just a positive one. So now let's sketch that with a different color. So a slope of 1 would be something like that. The next point they give us is the 0, 1. So 0, 1, dy dx, the slope, would equal 2 times 0 minus positive 1, which means the slope is -1. So that would look something like that. The third point is 0, 2. So dy dx is just equal to 2 times 0 minus a positive 2. So the slope is -2. So -2 would be like that. Now we can move on to when x is equal to 1. This point, 1, -1, would mean that dy dx is equal to 2 times the positive 1 minus the -1, which is a slope of 3. So a slope of 3 would look something like that. The next point, 1, 1, dy dx would equal 2 times 1 subtracted from a positive 1, or subtracted by rather, which means that the slope here is just 1. So this would be the same slope as this point right here. Something like that. And lastly, you have the point, let me move this, the point 1, 2, that's the wrong color, the point 1, 2, so dy dx would equal 2 times 1 minus 2, which is equal to 0. So the slope at this point would just be a horizontal line. And that would be part A. Part B asks, find the second derivative in terms of x and y. Determine the concavity of all solution curves for the given differential equation in quadrant 2. Give a reason for your answer. So this complex looking fraction here is just notation for the second derivative. So in essence, the derivative of this equation. So let's move everything down here. For part B, they want the second derivative of dy dx is equal to 2x minus y. In order to take the second derivative of this equation, first you have to take the derivative of both sides. So the derivative of a derivative becomes the second derivative. Now, the right side, the derivative of 2x with respect to x would just be 2. The derivative of a negative y with respect to x would actually be a negative dy dx. And this is actually a callback to implicit differentiation, when you take the derivative of a variable with in respect to an unlike base. So now that we have these two equations to work with, we can see, let's see what we can do with them. We can see that we can substitute this dy dx for this dy dx. So let's do that here. So the second derivative, d2y dx of 2, is equal to 2 minus the quantity 2x minus y, which can be further simplified down to just 2 minus 2x plus y. Now, the second part of the question, or the part rather, asks us to determine the concavity of all solution curves for the given differential equation in quadrant 2. And to give a reason for our answer. So remember that the concavity of a function is determined by the sign of its second derivative, not the sign as in the trig function, but the sign as in positive or negative. And that is actually what we're working with right here, the second derivative. So in essence, what this question is asking is, in all solution curves in the second quadrant, is this value positive or negative? So in the second quadrant, this is the second quadrant, we know that all the x values here are negative. And we know that all the y values here are positive. So x is always less than 0, and y is always greater than 0 in quadrant 2. Now if x is always negative, then that means this term here is always positive, because a negative times your negative x becomes positive. 2 is never going to become negative because it's a positive real number. And the plus y, you're always adding another positive number. So this entire expression will always be positive. Therefore, you can conclude that d2 of y divided by dx2, the second derivative of this function, is always positive. Always positive. And if the second derivative is always positive, that means that the function, that the base function, rather, is always concave up. Oh, that's ugly. Always concave up in quadrant 2. Part C asks that that y equals f of x be a particular solution to the differential equation with the initial condition f of 2 equals 3. F of 2 equals 3. Does f have a relative minimum, a relative maximum, or neither at x equals 2? Justify your answer. So remember that relative minimum and relative maximum only take place at two places, the endpoints and the critical points. And the critical points are where the first derivative, in this case, that's what we have right here, is equal to 0 or does not exist. So with the point they give us, the point 2, 3, let's test if this is equal to 0 or does not exist. So part C, dy dx equals 2x minus y. The point they've given us was to evaluate at 2, 3. So dy dx evaluated at 2, 3 is 4 minus 3 equals 1. And 1 is not equal to 0 and does not exist. So therefore, we can conclude that at the point 2, 3, there is neither a max nor a min. So part D asks, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So for part D, let's play around with some equations and see what we can figure out. So we know that the answer has to be in the form y equals mx plus b, where m and b are your constants. However, remember that our equation, dy over dx equals 2x minus y, is a differential equation. So let's take the derivative of this equation so we can have two differential equations and see what similarities we can find. So if we take the derivative of the left side with respect to x, this becomes dy over dx equals the derivative with respect of, to x of mx plus b. And we know, if we look here, the derivative of any constant is 0, and the derivative of anything multiplied by an x, which is what you're taking the derivative by, is just this coefficient. So this is just equal to m. Now, take a look at these two equations here. We have dy dx is equal to all of this, which is equal to m, and dy dx is equal to 2x minus y. So what we can do is we can substitute for dy dx and set them equal to each other. So m is equal to 2x minus y. 2x minus y. Now, because the question wants the answer in the form y equals mx plus b, let's rearrange this equation we have into this format. So this becomes y is equal to 2x minus m. Now let's once again put these two equations side by side and take a look at them. Y is equal to mx plus b, as given by the first equation, and y is also equal to 2x minus m, as given by the second equation. So now let's recap on the relationships we've established in this problem. We know that that y equals mx plus b is a solution to dy dx equals 2x minus y. And we also know that this dy dx is the differential equation of y equals mx plus b. So therefore, we know that this dy dx and this dy dx, the two differential equations with blue asterisks next to them, model the same relationship. And the solution to both of these relationships that we have here is also equal to the solution that they proposed in the original problem. So if we know that these two equations model the same mathematical relationship, that means at any point, this x value is the exact same as this x value, and this y value is the exact same as the second y value. Therefore, we can assume that these coefficients and these constants are the exact same. So from this, we can conclude that 2 is equal to m, and b is equal to negative m. We've already established that m is 2, so b is equal to negative 2. So now let's take a look at question 5. Question 5 reads, the figure above shows the graph of f prime, the derivative of a twice differentiable function f on the interval -3 to 4 inclusive. The graph of f prime has horizontal tangents at x equals -1, 1, and 3. The areas of the region bounded by the x-axis in the graph of f prime on the intervals -2 to 1 inclusive and 1 to 4 inclusive are 9 and 12 respectively. Part A asks us to find all the x-coordinates at which f has a relative maximum and to justify our answers. So, like we've established before, we know that relative maximums occur at critical points. And for this problem, we can disregard the endpoints because we know that if they're looking for a relative maximum, the function does not have an endpoint, or else it would have an absolute maximum and minimum. So critical points are when f prime of x is equal to 0 or does not exist. So in order to solve this part, let's take a look at all the critical points in this graph of f prime. Remember, if we're given f prime, then we just need to find where it equals 0 or it doesn't exist. Looking here, there's nowhere where f prime does not exist, but there are several places where it equals 0, at -2, at 1, and at 4. So now that we've found all the critical points of this function, don't jump the gun just yet and put all of these x values as when f has a relative maximum. Remember that at relative maximums, the first derivative, f prime, has to go from positive to negative. That's why at maximums, you see the derivative being positive at this end. The derivative is positive at this end, And at this point, at the maximum, once you cross it, the derivative turns negative. So let's take a look at the graph of f prime to see where the maximum are. So the first derivative is positive before negative 2 and negative after it passes negative 2. So we know because it goes from positive to negative, then this must be a relative maximum. At the point x equals 1, the derivative starts negative and ends up negative. So because there's no sign change, we know that this is not a relative extrema. And lastly, at the point x equals 4, the graph doesn't actually continue, so it cannot be a relative maximum nor minimum. So there's no extrema there. So we can safely answer that x equals negative 2 is the only max because it satisfies the above two conditions. Part B asks, on what open intervals contained in -3 to 4 exclusive is the graph of f both concave down and decreasing? Give a reason for your answer. So for part B, remember that decreasing means that the first derivative is negative. And concave down means that the second derivative is negative. Recall also that the second derivative of f is just the slope of the graph of f prime. So let's call this one blue and this one purple and see what intervals seem to satisfy both conditions. So the graph is decreasing, or f prime is negative, on the interval from -2 to 4. The graph is concave down, or the slope of f prime is negative, on the interval -2 to -1. It's positive here, then 1 to around 3, and then it's positive to 4. So these regions overlap here from -2 to -1, and here from +1 to +3. So on the intervals from -2 to -1 exclusive and +1 to +3 exclusive is the graph of f concave down and decreasing. Oh, oops, I'm getting too far ahead of myself. This is still part B, so part B comes all the way down here. Now on to part C. Part C asks, find the x-coordinates of all points of inflection for the graph of f. Give a reason for your answer. So points of inflection are when the second derivative of a function changes signs. So to go from negative to a positive second derivative, we know that the second derivative has to cross 0. So let's take a look at all of the places where the second derivative is 0. That is, the horizontal tangents of f prime. And they give them to us in the question. It says the graph of f prime has horizontal tangents at -1, right there, 1, right there, and 3, right there. And maybe I should use a different color. -1, 1, and 3. Now all we need to verify is that the graph changes signs, or the slope changes signs, at all three of these positions. So the slope comes into -1 negative and leaves it positive. So this is a point of inflection. At x equals 1, the slope comes into it positive and leaves it negative. So this is also a point of inflection. And lastly, at x is equal to 3, the slope comes in negative and leaves positive. So this is also a point of inflection. So we can say, for part C, at x equals -1, 1, and 3, these are all points of inflection because f prime's slope, or f double prime, changes signs. Part D asks, given that f of 1 is equal to 3, write an expression for f of x that involves an integral. Find f of 4 and f of -2. So let's think about part D for a second here. We know that we're given the initial condition that f of 1 is equal to 3. So we know that we have to use x is equal to 1 as our initial condition. We also know that an expression for f of x would be the integral, or the antiderivative of f prime. So let's create an antiderivative or an integral expression using this initial condition. So part D, our initial condition is the point 1, 3 when x is equal to 1, y is equal to 3, right? Yes. So our initial condition is 3 plus the integral from 1 to whatever number to x of f prime of a different variable t dt. In essence, what we're doing is starting at the lower bound of 1, so we can use this initial condition, and then taking the antiderivative of f prime of t evaluated at x equals this variable x. Now the second part of the question asks us to use this expression to find f of 4 and f of -2. So f of 4 and f of -2. Now all we need to do is plug in 4 for x and -2 for x. So let's use 4 as magenta, and we'll pick a nice dark blue for -2. So f of 4 is modeled by the initial condition 3 plus the definite integral from 1 to 4 of f prime of t dt. We know that this definite integral here is just the area under the curve of f prime from x equals 1 to x equals 4. And luckily for us, that information is in the problem. It says that the area under the curve of f prime on the intervals -2 and 1 inclusive and 1 and 4 inclusive are 9 and 12 respectively. So that means from 1 to 4, this area right here, and I know it's getting hard to see, this area right here is 12. But remember, because the area here is 12, that doesn't mean that the value of the integral is 12. In fact, the value of the integral would be the negative area here, because this is under the x-axis. So the value of the integral would actually be -12. So down here, this is -12, meaning that the value of f of 4 is just 3 minus 12 equals -9. We can do the same thing for the value of f of -2. So f of -2. F of -2 should equal the initial condition 3 plus the definite integral bound by 1 and -2 of f prime of t dt. Now, like we've encountered in the 2016 FRQ, when we have this kind of upside down, let's call it an upside down integral, where the initial bound is not at the bottom but at the top, we can use basic properties of integrals and rewrite it as 3 plus the negative integral, this time of starting at -2 and going to 1 of f prime of t dt. Now we can go back to the question and see what the area under the curve of the interval -2 to 1 inclusive is. According to the question, this area from -2 to 1 is 9. From -2 to 1, once again, we see that the area is actually, well, it's theoretically negative. The value of the integral is negative because the area is under the curve. So therefore, we can evaluate the integral here as -9. The negative of a -9 is just +9 plus your initial condition 3 equals 12. So we can say that f of -2 is equal to 12. Now last question for the video. Question 6 asks us to consider the curve given by the equation y cubed minus xy equals 2. It can be shown that dy dx equals y over 3y squared minus x. Part A asks to write an equation for the line tangent to the curve at the point -1, 1. Remember two properties about the tangent line. The tangent line intersects with this curve at this point and has the same slope of the curve at this point. Therefore, we can solve for the slope of the tangent line by using dy dx equals y over 3y squared minus x evaluated at the point -1, 1. This is equal to 1 over 3 minus -1, which is just 1/4. Now that we have the slope, this is the slope of the equation of the line. We also have the point. So let's use point slope form. Point slope form is y minus y1, y1 is 1, equals your slope, m, times x minus your x value, which is -1. So minus a -1 becomes +1. So this is your answer to part A. Part B asks to find the coordinates of all points on the curve at which the line tangent to the curve at that point is vertical. So if the tangent line slope is vertical, that means the slope does not exist, meaning that at these points that you're trying to get us to find, dy over dx, the slope of the graph, also does not exist. Because dy dx is a fraction, we know that the only time dy dx is not going to exist is when the denominator equals 0. So let's solve for when the denominator is equal to 0. So 3y squared minus x should equal 0. We can rewrite this equation as positive x equals 3y squared. Now this expression models when the tangent line is vertical, and this expression models the relationship of the curve. So to find when the line tangent to the curve at that point is vertical, you would find the intersection of these two lines. That is, you would have to solve a systems of equations with these two equations. So we can use substitution by substituting in this x for this x. So this equation becomes, let me keep it up there, this equation becomes y cubed minus the x, which is equal to 3y squared, times y equals 2. Now we can simplify. This y comes into this parentheses, making this y cubed. So this becomes y cubed minus 3y cubed equals 2, meaning y is equal to -1. Now that we know y is -1, we can find the other point on the curve by using this equation here. So let's evaluate y cubed minus xy equals 2 at y equals -1. So this becomes -1 cubed minus x times -1 equals 2. So this becomes -1 plus x equals 2. So x is equal to 3. So the answer to part B is 3, -1. Now part C asks us to evaluate the second derivative at the point on the curve when x is equal to -1 and y is equal to 1. So, we know we're given dy dx, the first derivative, and this is equal to y over 3y squared minus x. And we want to find the second derivative. To find the second derivative of this equation, you would just take the derivative of both sides. So the derivative of the derivative would be just the second derivative. And then for the derivative of this fraction, you're going to have to use the quotient rule. So remember that the quotient rule tells you to first keep the bottom as it is, then take the derivative of the top. So the derivative of the top, y, with respect to dx, would just be dy over dx. Then we subtract this from the opposite now. We keep the top, y, and we multiply it by the derivative of the bottom. So to find the derivative of this term, 3y squared, we'd use the chain rule. So first we take the derivative of the function on the outside. This is 6y, and then we take the derivative of the function on the inside, which is a y. So the derivative of y with respect to dx is dy dx. Now, oops, I shouldn't have closed the parentheses. Now, we take the derivative of the second term, the negative x. We know that this is actually a -1x, and the coefficient in front of the x when we take the derivative is -1. So this is just -1. And then the last step in the quotient rule is to divide all of this by the bottom squared. So this is 3y squared minus x, the quantity squared. We can simplify the dy's that we have inside the equation by plugging in our original condition that dy over dx is equal to y divided by 3y squared minus x. So we can rewrite this as 3y squared minus x times y over 3y squared minus x minus y times 6y times y over 3y squared minus x minus 1 over 3y squared minus x squared. And this has to be evaluated at the point -1, 1. Now, usually I'd show you some sort of work about how I got my answer, but for the sake of time, just plug these values in, this for x and this for y, and you get 1 over 32. And that was the 2015 AP Calculus AB FRQ completed. If you have any questions, be sure to drop it down in the comments and leave a like or subscribe if this video helped you.